James Webb has brought a new infrared perspective to Betelgeuse, one of the most famous and unstable-looking stars in our night sky. And the details surrounding this red supergiant are forcing astronomers to look more carefully at what they thought they understood. Betelgeuse sits on the shoulder of Orion and shines hundreds of light years away. Yet it is close enough that astronomers can study its changing surface and the material it throws into space. That makes this star something unusual in stellar astronomy, a massive star whose evolution can be watched in remarkable detail. And when scientists first began comparing the behavior of Betelgeuse across different wavelengths, the picture was not as simple as a star merely getting brighter or dimmer. Researchers immediately noticed something unusual. The star's outer environment can change dramatically, while its enormous surface is itself restless and uneven. That detail matters. For decades, astronomers believed the basic story of a massive red supergiant was relatively straightforward. A star like Betelgeuse begins its life burning hydrogen in its core. Over millions of years, that fuel is gradually consumed. Eventually, the star evolves into a much larger and cooler phase, expanding until its outer layers become enormous compared with the Sun. Betelgeuse is now in that late stage of stellar evolution. Its reddish appearance comes from its comparatively cool surface temperature, around 3,500 Kelvin, far cooler than the Sun's roughly 5,800 Kelvin surface temperature. But cool does not mean calm. A red supergiant can be violently dynamic, with enormous convection cells moving energy from deep inside the star toward its surface. Imagine a pot of water boiling, except the bubbles can be larger than planets. The comparison is imperfect, but it gives you a sense of the scale. And Betelgeuse has already shown us just how unpredictable that outer atmosphere can become. In late 2019 and early 2020, the star underwent what became known as the Great Dimming. From Earth, Betelgeuse appeared dramatically fainter than usual. For a short time, astronomers had to consider several possibilities. Was the star's surface cooling? Had something changed in its atmosphere? Was dust blocking part of its light? The evidence eventually pointed toward a combination of physical processes, including a powerful episode in which material was expelled from the star and later formed dust that obscured part of its visible light. The event became a rare opportunity to watch a massive star physically rearrange its outer layers. But that episode also exposed a deeper problem. We still do not fully understand how stars like Betelgeuse lose mass. That is where infrared astronomy becomes especially important. Visible light tells us what the star looks like to human eyes, but infrared light can reveal something different. Infrared wavelengths are sensitive to cooler material, including dust and gas surrounding a star. They can also pass through some of the obscuring material that makes visible observations more difficult. NASA designed the James Webb Space Telescope around this kind of infrared vision. Webb can observe near-infrared and mid-infrared wavelengths, allowing astronomers to investigate regions and processes that ordinary visible light images cannot show as clearly. It is not simply a more powerful camera, it is seeing the universe in a different part of the electromagnetic spectrum. That distinction becomes critical with Betelgeuse. The star itself is so bright and extended that observing it is not like photographing a distant galaxy. Its brilliance can overwhelm the detector, and its apparent size makes the surrounding environment equally important. Astronomers have to think carefully about exposure, filters, calibration, and the way the data are processed. A beautiful astronomical image is not a photograph in the ordinary sense. It is a visual representation of measured light, often combining observations made through different filters. The colors you see can correspond to different infrared wavelengths rather than colors a human eye would naturally perceive. So when you look at a Webb image of a cosmic object, you are really looking at translated information. And with Betelgeuse, that information can become remarkably revealing. The star is not a perfect sphere. Its surface is dominated by enormous convective structures, regions where hot material rises while cooler material sinks. Those movements can change the brightness and appearance of the stellar surface over time. They can also influence how material escapes into space. This is one reason Betelgeuse is so scientifically valuable. We know that massive stars return enormous amounts of material to their surroundings before they eventually die. But the exact mechanisms controlling that mass loss remain an active area of research. In more than 25 years of studying the universe, one lesson becomes increasingly clear. The most interesting discoveries often come from objects we thought we already knew. Betelgeuse is a perfect example. Astronomers have studied it for generations, yet every new observation can expose another layer of complexity. There is another reason this star attracts so much attention. Betelgeuse is expected to end its life as a supernova, but that does not mean an explosion is imminent. Its final timeline cannot be predicted with precision from the observations we have today. Astronomers understand the broad stages of massive star evolution, but they cannot look at Betelgeuse and assign a reliable countdown to its death. It could be relatively soon on astronomical timescales, or it could still be many thousands of years away. That uncertainty is important because dramatic headlines can easily turn a fascinating stellar process into something it is not. The real story is more interesting. Betelgeuse is giving scientists a chance to investigate the physical processes that eventually shape a supernova before the explosion itself occurs. Material leaving the star carries elements produced inside it. Dust formed in the surrounding environment can later become part of the raw material from which future stars, planets, and other structures form. In that sense, a dying massive star is not simply disappearing, it is returning chemically enriched material to space. And the strange features around Betelgeuse may hold clues about exactly how that happens. Previous observations have already shown plumes and asymmetric structures extending away from the star. Infrared observations have revealed dust surrounding Betelgeuse, while high-resolution observations at other wavelengths have shown that its surface and atmosphere can change over time. The challenge is connecting these observations into one physical story. Why does material escape in some directions more strongly than others? How do giant convective cells affect the star's atmosphere? How quickly does expelled gas cool? When does dust form? And how does that dust interact with the radiation streaming outward from the star? Those questions are not cosmetic details. They affect how astronomers model the final stages of massive stars. Webb's infrared capabilities give researchers another piece of that puzzle, especially because infrared observations can trace cooler material and molecular signatures that are difficult to study in visible light. Different wavelengths effectively provide different layers of information. One wavelength may emphasize the hot stellar surface. Another can reveal cooler gas. Still another can highlight dust farther from the star. Put those layers together, and Betelgeuse begins to look less like a simple glowing red sphere and more like a constantly changing stellar environment. The pattern is more complicated than expected. And this is where the new imagery becomes scientifically interesting. The important question is not simply whether the image looks dramatic. The important question is what the structures represent physically. Are we seeing temporary features created by the star's convection? Are we seeing material from a previous outburst? Could dust and gas be distributed unevenly around the star? Or are several of these processes happening at once? Astronomers have learned from the Great Dimming that Betelgeuse can produce large-scale changes surprisingly quickly. The star's atmosphere is capable of ejecting material, cooling it, and altering the amount of light that reaches us. That means a single image is only one moment in a much longer sequence. To understand what is happening, researchers need observations separated in time, across multiple wavelengths, and with carefully calibrated measurements. This is why a new infrared view can be more valuable than simply producing a sharper picture. It can be compared with older observations, and with observations from other telescopes. The goal is to determine what changed, what stayed stable, and which structures move with the star's enormous atmospheric cycles. And one overlooked detail may be especially important. The material around Betelgeuse is not merely leftover debris. It is part of the star's ongoing interaction with its surroundings. The gas and dust being released today can eventually become part of the interstellar medium, where future generations of stars and planets may form. That gives this observation a much larger meaning. We are not simply watching a famous star shine. We are watching a massive star lose pieces of itself, while astronomers try to understand the physical machinery driving that loss. Webb gives us another way to see that machinery, but the image alone cannot answer every question. The evidence confirms that Betelgeuse is dynamic, that its atmosphere contains complex structures, and that its surrounding material changes over time. What remains uncertain is how all of those processes connect. That is the scientific mystery worth following, because hidden within the structure around Betelgeuse may be the clearest clue yet to how a massive star prepares itself for the final transformation that lies ahead. The most likely explanation for the strange appearance around Betelgeuse is not something exotic, but the star's own unstable atmosphere, where enormous convection, expelled gas, and newly formed dust can create structures that change with time. The important point is that infrared observations can reveal layers of this environment that visible light does not show as clearly. Betelgeuse is not a smooth red ball with a simple outer edge. Its atmosphere is extended, turbulent, and constantly moving, and different wavelengths can make different regions visible. That distinction is important. When astronomers study a star like Betelgeuse, they are not looking at one surface in the ordinary sense. They are looking through layers of gas, each with different temperatures, densities, and chemical properties. Near the visible surface, enormous convection cells can transport heat upward. These structures are thought to contribute to the irregular bright and dark regions observed across the star. Farther out, the gas can cool enough for molecules and dust-producing material to become important. Once dust forms, it can absorb and scatter some of the star's light, changing what observers on Earth see. This is one reason Betelgeuse has never behaved like a textbook sphere. To understand the scale, picture a star hundreds of times wider than the Sun, with atmospheric structures that can extend across enormous portions of its surface. Now imagine that material moving outward from that star and cooling as it travels. The process is not happening over a few miles, or even a few million miles in a neat, uniform shell. It unfolds across a vast, changing environment around a star, so large that its outer layers would extend far beyond the orbit of Mercury if Betelgeuse occupied the Sun's position. From our perspective, all of that complexity is compressed into a tiny point of light. But infrared astronomy allows scientists to separate some of those layers. The evidence supports a remarkably active environment. Earlier observations of Betelgeuse have already shown that its surface can develop bright regions and irregular structures, and that those features can look different when observed at different wavelengths. Infrared observations are especially useful because cooler outer material can become more prominent there. This does not mean infrared light simply gives us a photograph beneath the star's surface. It means different wavelengths interact with the star's atmosphere in different ways, allowing astronomers to sample different physical conditions. That is a subtle distinction, but it changes how you interpret the image. The James Webb Space Telescope was built to study infrared light with extraordinary sensitivity. Its instruments can separate wavelengths that correspond to different physical processes, and its observations can be compared with data from other observatories. For a bright nearby star like Betelgeuse, that comparison is essential. A feature that appears in one wavelength but not another may tell astronomers something about temperature, molecules, dust, or the depth from which the light is emerging. And that is where the real scientific value lies. The unusual detail is not necessarily a single mysterious object sitting beside Betelgeuse. The more compelling possibility is that what looks unusual is part of a changing relationship between the star's surface, its atmosphere, and the material it has already expelled. Researchers know that Betelgeuse loses mass. What remains difficult is understanding exactly how that material is lifted away from the star and how the process varies over time. One possibility researchers examine is that giant convection cells play a major role. Deep inside a red supergiant, energy moves outward through enormous currents of hot plasma. When those currents reach the surface, they can create regions that are hotter or cooler than their surroundings. Because Betelgeuse is so extended, these structures can become enormous compared with anything we see on the Sun. They may also contribute to pulsations and atmospheric disturbances that help move material outward. But convection may not tell the whole story. The atmosphere of a red supergiant is relatively cool compared with the star's interior, and as material rises and expands, it can lose energy. Eventually, molecules and dust can form in the outflowing material. Radiation from the star then interacts with that dust. In simple terms, the star's light can push against tiny grains, helping transfer momentum to them. The dust can then drag surrounding gas outward. This is one of the important mechanisms astronomers consider when explaining how evolved giant stars shed their outer layers. The evidence points somewhere specific. The dramatic dimming Betelgeuse experienced beginning in 2019 provides an important example. Observations indicated that the star had experienced a substantial surface mass ejection event, followed by cooling and dust formation that obscured part of the visible light. That event demonstrated that Betelgeuse can rapidly alter its immediate surroundings. It also showed why studying the star only in visible wavelengths can provide an incomplete picture. If you enjoy exploring discoveries like this through clear, evidence-based science, consider subscribing so we can keep examining the universe together, one observation at a time. Because Betelgeuse gives us something rare, a chance to study the late life of a massive star before its final transformation. We cannot observe the future, but we can observe the processes leading toward it. That is where the broader significance becomes clear. Massive stars are factories of elements. During their lives, they build heavier elements through nuclear fusion, and when they lose material through stellar winds or dramatic outbursts, some of that material enters surrounding space. Eventually, that enriched material can become part of new stars, planets, asteroids, and other structures. The atoms in future worlds can therefore carry a history that began inside earlier generations of stars. Betelgeuse is giving astronomers a closer look at one stage of that cycle. In more than 25 years of following deep space discoveries, one pattern stands out. Scientific understanding rarely arrives from a single spectacular image. It develops when independent observations begin agreeing with one another. A new image becomes more valuable when researchers can compare it with older measurements, spectra, visible light observations, radio data, and future observations. That is how a beautiful picture becomes evidence. And Betelgeuse is particularly well suited to this approach because it changes. A static object gives astronomers one set of conditions. A variable star gives them a sequence. By observing Betelgeuse repeatedly, researchers can ask whether a structure moves, fades, expands, cools, or disappears. If a feature changes in a predictable way, that can reveal its physical origin. If it behaves differently than expected, the model may need to be adjusted. This is how science advances. There is another important point about Webb's infrared vision. The colors presented in many astronomical images are not necessarily the colors your eyes would see. Infrared wavelengths lie beyond the visible range, so scientists assign visible colors to different infrared bands to make the data understandable. A bright red or orange region in a processed image may therefore represent strong emission at a particular infrared wavelength rather than a literal red cloud floating in space. That does not make the image artificial. It makes it translated. The telescope measures light. Scientists turn those measurements into an image that allows us to see patterns our eyes cannot detect directly. In the case of Betelgeuse, those patterns can help reveal differences in temperature, dust distribution, and the structure of the surrounding material. But the data does not yet rule out every alternative interpretation. Some features may be connected to convection. Others may reflect material expelled during earlier episodes of enhanced mass loss. Some could be related to dust formation or changing conditions in the outer atmosphere. And because Betelgeuse is evolving on timescales that overlap with our own observations, astronomers need repeated measurements to determine which structures are temporary and which represent longer-lasting patterns. That uncertainty is not a weakness. It is the normal state of serious astronomy. What experienced astronomers learn is that uncertainty becomes useful when you can identify exactly what remains uncertain. We may know that a structure exists without knowing precisely how it formed. We may know that dust is present without knowing how the dust distribution changed during a particular event. We may understand the broad physics while still missing details about the timing and interaction of several processes. Those missing details are where future observations become valuable. A new generation of infrared observations can be compared with measurements collected before and after major changes in Betelgeuse's brightness. Spectroscopy can reveal the chemical fingerprints of gas and molecules. High-resolution observations can help track surface structures. Other telescopes can observe wavelengths that Webb does not specialize in. Together, those observations create something much more powerful than any single image. They create a time-dependent portrait of a dying massive star. And that portrait may eventually help answer one of the larger questions in stellar astrophysics. How exactly does a massive star transition from a stable-looking object into a rapidly changing final stage of evolution? We already understand much of the broad sequence. We know that Betelgeuse is a red supergiant. We know it is losing mass. We know its surface is dynamic. We know dust and gas surround it. We know that its brightness can change dramatically. What remains difficult is connecting those pieces into a complete physical model. The answer will not come from speculation. It will come from more evidence. When researchers examine data like this, they are looking for consistency. Does the same structure appear at multiple wavelengths? Does it move as expected? Does its temperature match the proposed explanation? Does the surrounding dust respond in a way predicted by stellar wind models? These questions turn an intriguing image into a scientific test. And there is something deeply satisfying about that process. The more closely we examine Betelgeuse, the less it resembles a simple glowing star, and the more it becomes what it truly is, a massive evolving physical system, changing from one moment to the next. The strange detail in the infrared is therefore valuable, not because it proves something impossible, but because it gives scientists another piece of a much larger puzzle. Webb is helping reveal how the outer layers of a massive star behave, how material escapes, how dust develops, and how stellar evolution unfolds in real time. Future observations may sharpen that picture further, especially when new infrared measurements can be compared with observations across the electromagnetic spectrum. For now, Betelgeuse reminds us that even one of the most familiar stars in the sky can still contain details we have not fully understood. And sometimes the most important discovery is not finding something completely new, but finally seeing a familiar object clearly enough to ask a better question.